Dun 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 dun. We're going to look at regression for how much damage a laptop takes based off how high it was dropped from. Super low, low, medium, high, super high. 5 different groups, each with their own average. We could do ANOVA on this. We've talked about how. But looking at that picture, it wouldn't be too hard to change these averages to be in a line for regression. And we could still do the same techniques that we've used with ANOVA to find out how far each data point is from the predicted level. Instead of being some X bar, it's going to be a prediction, which is going to come from our beta naught plus beta 1x. We're putting hats on to say these are estimates. So I need a y hat to talk about this guy being a predicted value, just like the averages were before. We want an overall average, which is y bar, the average of the y values. And notice this guy isn't like the average of everything. He's really the regression line when the slope is 0. So as we're testing using ANOVA, what this is going to tell us is whether the prediction line is significantly different from 0. The same test we did with regression, but from an ANOVA standpoint. So being like ANOVA, but having y values and x values, whereas before it was just different categories, some of the notation is a little different. So let's be really clear. Before we had xij, group I that jth one, now we're going to have an xi, yi coordinates. And this yi is going to be really important because he's the value saying how far away we were from the regression line. Regression residuals are in the up and down direction. So that yi is going to be the important player. Then we had x bar I, individual averages for each group. Now we're going to have y hat i's, predicted values on the regression line. And the way we calculate those is with our beta naught hat plus beta 1 hat times the x values. So that's where the x values come in, is in making the prediction. We also have an overall average. We used to call that x bar, but now x is actually an axis that we're using to keep track of where we are in our data, and so it's on the y-axis, meaning y bar. So we can look at our equation, for example, SSG, which used to be the average to the data point. We did that across all the data points. It was the same value because they were grouped up across all the groups. Now that we're talking about regression, I can write this as y hat minus y bar, the value on the prediction line from the overall average. And I don't need to say do it for all the data points in the group across all the groups because we don't really have groups. They're just stretched across the x-axis. So all I need to say is to do this across all the data points.
I want them all activated. Wait, all of them at the same time? You heard me.
What does this represent on our graph? It's the distance from the regression line to the average for each of these dots. It's a big distance for the dots out on the edge. These dots in the middle, we're talking smaller distances. These dots over here, big distances. But for each dot, how far away was the regression line? You can think of it like a spring. How hard would it be to twist this regression line up if it was attached by springs to this y bar? That's a measure of the force needed to get that regression line. That's what SSR is trying to measure. The other piece that we need to look at is the SSE, which used to be from the data point to its average. Now it's from the data point to the regression line. These dots here are far away, this dot's close, that dot's close, further out, close, and further out. That's SSE. It used to be measured as each data point minus his average. Now under regression, it's going to be each data point minus his predicted value. And we don't have to keep track of groups anymore. It's just do that across all the data points. This y hat I, we could have written it out with the prediction equation. It just looks bigger that way. I don't know if you want that in your notes, you're welcome to. It just makes the equation look longer. And I don't have a lot of room left on my board, so I'm going to strike it. And now move on to SST. And if you followed the way I've been doing this, it's not going to be hard to see. Individual data point minus overall average can be written as the yi's minus the y bar, which on the picture is going to be from the data point all the way to the blue line, the flat line. How far is the data point from being flat in regression? Those guys long, these guys short. This data point was right next to the blue line, so not very far at all. So we have the old ones and the new ones. Let's only look at the regression one here. And Before I move them onto the ANOVA table, I want to shift them up so I have a little more room on this board. And I'm getting a little lazy. I'm not putting the I equals 1 to n because this is just sum across all the data points, yi minus y bar, okay? We are ready to look at our ANOVA table. We don't have groups anymore, so we don't call it G for groups. What do we call it? How about R for regression? That's why I called it SSR instead of SSG. The wording really doesn't matter. I've also seen SSM. There's a bunch of weird letters people use. Whatever you need to say, this is what we're trying to test. But we don't have groups, so K minus 1 doesn't make sense. For regression, this is always a 1 right there. That's a rule, just 1. And there's reasons for it, right? We're testing an intercept and a slope, so that's 2 minus 1. But just learn 1 goes right there.
You remember this one, right?
This is going to be n minus 2. That's the degrees of freedom you're used to from using the applet when you do regression. And then here is n minus 1, which it might not surprise you, n minus 1 shows up because that's so very common when we talk degrees of freedom. And then we talked about how to do SSR, SSE. All these other pieces work just the way that we're used to for ANOVA. 2 interesting pieces that come out of this table. One is right here. This MSE is a measure of how spread out the data is from the regression line, often called the sigma for regression, the residual standard error. This is how you calculate that straight from this MSE. Of course, this is variance. If you took the square root of that, then you'd be talking about standard deviation or standard error. Also, here is the total variability, how far those data points were from the flat regression line. Here's how much variability there was in the regression line. So if you took a ratio of these two, you'd have a measure for how much of the variability is explained by the model. That's R squared. This is how you calculate it. And if this is a little hard to see, remember that SSR and SSE add together to make SST. So you can simplify this equation, SST minus SSE, which, dividing the fraction, gives us a 1 minus SSE over SST. And that's like saying, here's 100% of the variability. Take away the variability from the data around the regression line, and what's left is the percent variability explained by X. So that's why I wanted a little more room on this board to write a few of these pieces, because those are important, cool pieces we get by looking at regression from ANOVA. And this gives us the same answer as when we do regression with the t-test. In fact, if you take the t-test and square it, you get the f-test. So in some cases, you could do this both directions and make sure that you're getting the same thing. That would be like twice the work. I don't know why anyone would want to do that, but you could. We're doing the same thing we've done before, just from the ANOVA viewpoint.